Hello, welcome to the second lecture. Today actually we will start the formal discussion of the topics. In particular, we will consider what are the ideas that led people to consider quantization of energy, and later we will see why people also considered quantization of angular momentum. The two experiments, or rather two broad classes of experiments which led people to consider quantization of energy are blackbody radiation and photoelectric effect, and we will discuss these two topics today. The word blackbody radiation actually sounds rather awkward. Why blackbody? Because the objects which radiate energy, they are usually red or maybe yellow or white. Why we use the word black body? So let us try to understand that. First, one very simple observation which is known from ancient times: if you heat a body, especially a metal, it emits radiation. Any heated body, it emits radiation. And sometime in the 1800s, the spectroscopic techniques have improved. So people have studied the frequency of the radiation emitted by a heated body and found that there is actually a continuous distribution of the frequencies, starting from very low values to reasonably high values. And two simple observations, which first one is known for a long time: the hotter the body, the more radiation was emitted, but the spectroscopic studies have shown that the hotter the body, the higher is the frequency, higher frequencies are emitted more strongly. And we have seen, first, when you have seen pictures where you take a piece of metal and heat it, and it first becomes red hot and then yellow hot and it becomes white hot. And another important property which people have found in their study of this radiation is that the frequency of radiation is independent of the body that is being heated. For example, you take iron or you take another metal, of course, the temperature of the body should be lower than the melting temperature, otherwise the metal will melt. But you take iron or copper or any other metal and heat it to very high temperatures, and you find that the emission depends only on the temperature. It does not depend on the composition of the metal, which was very surprising, because when you do spectroscopy, you find that the spectrum that is emitted actually depends on the element, the composition of that object. But as far as this high temperature emissions are concerned, the composition of the material doesn't matter. What matters is only the temperature. So this was a puzzle, and the famous scientists in the 1800s, they have studied the problem. And also the science of thermodynamics was newly developed. It started around 1800, and by about 1870 or so, thermodynamics was very highly developed. So people applied thermodynamic arguments to study this blackbody radiation. In particular, Kirchhoff, whose name is very well known, especially for the electrical circuits laws, Kirchhoff's voltage law and Kirchhoff's current law, which we use to solve electrical circuits. The same Kirchhoff, he studied blackbody radiation and he proved a theorem using purely thermodynamical arguments. So, you take a black body and you consider it is emitting radiation from low frequencies to high frequencies. So, you look at the energy emitted in a single, you can't quite consider energy emitted at a single frequency. What you have to consider is the energy emitted in a small range of frequencies between nu and nu plus d nu. And this energy, actually what he considered was not quite energy, he considered power per unit area, that is energy per unit area per second, the power per unit area emitted in the range nu to nu plus d nu. He found that this is equal to the average incident power absorbed by this body in the same frequency range, which he called a nu d nu, multiplied by a function j, which depends both on the frequency and temperature. And what Kirchhoff proved is that this function j is a universal function. It does not depend on the material. It depends on frequency, it depends on temperature, but it does not depend on material. And this he proved theoretically. It's not a experimental observation, it's a theoretical proof which used thermodynamical arguments. We will not go into details of this proof, but we will take the Kirchhoff's law as it stands, which says that E of nu d nu is equal to this universal function j, which depends on frequency and temperature, multiplied by a nu d nu. Now, this a nu is the fraction of the power absorbed by the body, which can differ from material to material. And when you are doing theory, if you are designing an experiment or if you are designing a system where you want the body to emit radiation, yes, you need to worry about the details of what A of nu is. But in doing theory, you want to concentrate on the topic of interest, and so people who have done these studies, they have assumed that this A of nu is equal to 1. They made a simplifying assumption, but it's not that much of an assumption. You can actually have systems similar to that. I'll come to it in a minute. But A of nu equal to 1 is the definition of a black body. That is, it is a body which absorbs all the radiation which falls on it, and that's it. It doesn't reflect any. So, you have to keep the sort of energy balance, energy accounting here in mind. So, when radiation falls from an external source onto a body, typically some of it is absorbed and some of it is reflected. This we see all the time. For example, you take a piece of marble and you take a piece of black stone, you keep both of them in the sun, let's say for an hour or so, and after that you touch the marble, you find that it is still cool because the sunlight which is falling on the marble is being completely reflected, whereas the black stone, it absorbed all the sunlight and you would see that it has become much hotter. And having absorbed the sunlight, the temperature of the black stone has gone up, and since it's at a higher temperature now, it is radiating energy. So, there is energy going in and energy coming out, but the energy that is coming out is not being reflected, it is absorbed and then radiated out. So, we have to make this careful distinction between the energy inflow and energy outflow, and so both in the case of marble and in the case of black stone there is an energy outflow, but in the case of marble the outflow is due to reflection and that temperature of the marble remains low, whereas in the case of black stone the energy is absorbed which raises the temperature and then it is emitted as radiation because of the high temperature. So, it is a completely different process. Now, this is how we get a black body. In principle, we can make a black body out of any material. The figure shows one possibility. You take a material of arbitrary shape and you make a small hole in it and you assume that the radiation goes into the material only through the hole. It is an assumption, but it is possible. I can arrange it so that the radiation falls into the material, goes into the material only through the hole, and once it is in the hole, the radiation keeps hitting the walls of this material and gets reflected, and when it hits it, the radiation is partly absorbed and partly reflected, and the reflected radiation goes and hits the wall again, partly absorbed, partly reflected, and it keeps going on and on until all the radiation is absorbed. So, in that sense this material has now become a black body. So, in principle it is possible to model any material in the form of a black body. Therefore, in doing theoretical analysis people assume that okay, I take this material to be a black body. Now, let us leave Kirchhoff for a moment and talk about a different experiment. Now, it is an experiment, not a theorem. This is done by a physicist called Joseph Stefan. He studied the radiation from different materials, and each material he heated to different temperatures and systematically observed the total amount of power that was per unit area that was emitted by these materials, and he found that this total power is always proportional to the fourth power of the temperature of the body. So, as an equation we write E total is equal to sigma T power 4. Now, this sigma is called Stefan's constant and it has a value 5.67 times 10 to the minus 8 watt per meter square per Kelvin power minus 4. This again is sort of confirming what Kirchhoff has said. The radiation depends only on the temperature and does not depend on the composition of the material. So, in that sense the theorem proved by Kirchhoff and the observations made by Stefan, they are in agreement with each other. They both say that the radiation depends on temperature, does not depend on the composition. But of course, if you remember, Kirchhoff's law introduced that universal function J, which depends both on the frequency as well as on the temperature. So, Stefan's experiments showed that temperature dependence it's going as T power 4. So the next thing people tried to study is what is the temperature dependence of the radiation. By the way, it's an aside, a few years after Stefan's observation, Boltzmann actually derived Stefans' law again using thermodynamical arguments. We will not go into those details, but it's a great achievement, and in fact because of which this constant sigma is actually called Stefan-Boltzmann constant. As I said, the next topic people tried to look at is how exactly does the emitted power, how does it depend on frequency, and of course for radiation frequency and wavelength are related to each other. Frequency times wavelength is the speed of light. So you can choose to use either frequency as your variable or wavelength as your variable, and in the series of graphs that I will show, the plotting is done as a function of wavelength. So we talked about the work of Kirchhoff, we have talked about the work of Stefan and also of Boltzmann. So the next important person to make an important contribution to blackbody study is Wien, and like Kirchhoff and Boltzmann before, Wien also used thermodynamical arguments in the study of blackbody radiation, and he proved the following theorem, which goes under the name Wiens displacement law. The blackbody radiation, when you plot it as a function of the wavelength, by the way, radiation we describe either in terms of frequency or in terms of wavelength. So far I have been talking the emission as a function of frequency, but wavelength is 1 over frequency, so I can make a change of variable and I can talk about emission as a function of wavelength also. And blackbody, when it emits radiation, it emits over a wide range of wavelengths, and it starts from 0 at very low wavelengths, reaches a maximum, and then the emission falls off at longer wavelengths. So for a given temperature, you find that the blackbody emits maximum amount of intensity at a given wavelength. So this wavelength we label lambda max, and using thermodynamical arguments, Wien proved that lambda max times T, that is the temperature, lambda max times temperature is a constant. This is called Wien's displacement law, and you see the evidence of it in the plot. At smaller temperatures, you find that the peak emission occurs at larger wavelengths, whereas at larger temperatures the peak emission you see is occurring at smaller wavelengths. So this is an experimental observation, and Wien proved it as a theorem based on thermodynamical arguments. Wien also did something more. As I discussed earlier, Kirchhoff introduced this universal function J, and if we look back a few slides, we see that this universal function is equal to the power emitted by a black body per unit area. But power emitted by black body per unit area we can relate to the energy density that is the energy that is trapped in the black body per unit volume, and one can show again using thermodynamical arguments that these two should be proportional to each other, and one can in fact prove that this universal function introduced by Kirchhoff, which is the power emitted per unit area by the black body, is equal to the energy density in the black body, and just as that J is a function of frequency and temperature, this energy density is also a function of frequency and temperature. So, if J is a universal function, C is speed of light, which is also universal. Therefore, the energy density of a black body U, nu and T is also a universal function. So, one should be able to calculate it based on some first principles, especially thermodynamics. However, Wien took a shortcut. He used Stefans law. Stefans law said total emission summed over all frequencies goes as T power 4. So, he utilized this formula and he was able to show, he was able to derive starting from Stefans law that this energy density of black body, it should go as some constant times frequency cube times exponential minus some other constant times frequency divided by T. He was able to prove this formula starting from Stefans law. And if you compare Wien's formula to data, you find that until about 5 microns, the data fits very well with the theory, but above 6 microns, you find that the prediction of the theory is noticeably lower than the data points. So, Wien's derivation, it's very good. It explains the data to a large extent, but at longer wavelengths, it is beginning to, it differs from the data, the theory and data differ from each other more and more. In fact, if you look at this figure, you see the difference between theory and data much more in a more dramatic fashion. The curved line is what is predicted by theory, the Wien's law, whereas the straight line is a fit to the data. What is this data? Here, this in fact is a great advance that a group of spectroscopists in Berlin made. They were able to measure the spectrum of a black body at far infrared, that is at frequencies well below the visible frequency, which of course required improvement in spectroscopic techniques. And if you see this figure, you find that they have taken the data at the wavelength corresponding to 51 microns. That's a very large wavelength. I mean, a typical visible light will have sub-micron wavelength, and this is almost 100 times longer wavelength. So, one needed a completely different type of equipment to make these measurements. And what these people did is they took the measurement at one wavelength, but they varied the temperature. If you fix one wavelength, you fix the frequency also. They varied the temperature and found that there is a linear relationship between the emission and the temperature, whereas Wien's theory predicted that curve, and you notice that there is essentially no relation between Wien's prediction and the data when it comes to long wavelengths or low frequencies. So, this is a problem. I mean, if you have a theory, it should explain everything, not only part of it. So, question is how to make a modification so that the theory can explain both short wavelengths as well as long wavelengths. An attempt was made by two British physicists, Rayleigh and Jeans. They calculated the energy density of black body through using a different kind of argument compared to what Wien or Kirchhoff has used. They modeled the black body as if the walls of the black body contains a large number of oscillators, and an oscillator in which a charged particle is oscillating emits radiation and it can also absorb radiation. So, that is why they model the black body to the walls of the black body to consist of a Avogadro number of oscillators, and they assumed each oscillator oscillates at its own frequency. So, it emits or absorbs radiation at that frequency only. And how do we know this? That of course is predicted by Maxwell's theory of electromagnetism, and they further assume temperature of the black body is constant. So, they assume that the oscillators which make up the walls of the black body, they are in thermal equilibrium along with the radiation, and then they applied once again a thermodynamical argument and showed that there is a theorem in thermodynamics called equipartition theorem, and using this theorem they showed that average energy of these oscillators is k times T, where k is called the Boltzmann constant and T is the absolute temperature. And one can actually show how this theorem comes about, the equipartition theorem. Thermodynamics tells us that if something is at temperature T, then the probability of a component of it having energy E is proportional to exponential of minus E by kT. So, that is the probability and it should add up to 1. So, when I integrate it from energy 0 to infinity, that should be 1, and average energy is E times probability integrated from 0 to infinity. So, I do that and I calculate the average energy, and you can look up table of integrals to do these integrals, and you find that the average energy turns out to be kT. Now, another thing that Rayleigh and Jeans did is to calculate the number of oscillators oscillating with frequency nu. Again, what they did is the number of oscillators oscillating with frequency in the range nu and nu plus d nu, and that number they called n of nu d nu, and this calculation is a bit involved, and we will do this calculation, but somewhat later in the course. You please accept this result for the moment, and they got an answer 8 pi nu square by c cube d nu. So, the energy density of the black body is equal to the number density multiplied by average energy. So, they multiplied nu d nu with kT and they got the result energy density is equal to kT times 8 pi nu square by Cq. Now, this formula you notice it is predicting that the energy density is proportional to temperature, and if you remember we discussed earlier energy density is related to the emissivity, that is power emitted per unit area. Therefore, this prediction agreed with the measurement made by the scientists at Berlin that at long wavelengths the emissivity is proportional to the temperature, and that is what this predicts. However, it also predicts that for very small wavelengths or equivalently very large frequencies, it diverges. The average, the energy density of the black body, it goes off to infinity, which obviously is nonsense. So, we have this sort of funny situation where Wien used thermodynamical arguments and got an answer which worked at low wavelengths but didn't work at high wavelengths, whereas Rayleigh and Jeans, they also used thermodynamic arguments, but they got an answer which worked at large wavelengths but did not work at small wavelengths. So, both of them are partly right and partly wrong. So, how to resolve this tension? And that is where Planck came in, and Planck made this really radical proposal. Till then, people assume that when you change the energy of an object, it goes continuously from a low value to a high value, but Planck made this proposal that radiation is absorbed or emitted. A black body emits radiation only in certain quanta. What is this quanta? He said that a radiation with frequency nu, it has quanta of energy h nu, 2h nu, 3h nu, 4h nu, etc. and it emits radiation only in this integer multiples of h nu. And in this process, he introduced a new fundamental constant into physics called h, which we now call Planck's constant. And so he made this proposal. Then what use is this proposal? I mean, it sounds completely crazy and it goes in some sense against all the basic points of view of physics, that coordinates, momenta, energy, they should vary continuously. But here Planck said no, black body emits radiation in steps, either h nu or 2h nu or 3h nu, 4h nu, etc. So, how does Planck's hypothesis, how does it solve the problem? Well, again let's take Planck's hypothesis and apply it to Rayleigh-Jeans idea. I mentioned before that the probability of something having energy E at temperature T is given by exponential minus E by kT, where k is the Boltzmann constant. Therefore, now with Planck's hypothesis, this probability is exponential minus nh nu by kT. And let us now calculate the average energy. So, you have some n going from 0 to infinity, the value of energy nh nu multiplied by probability exponential minus nh nu by kT, and in the denominator we sum all the probabilities, that is sum n going from 0 to infinity exponential minus nh nu by kT. The denominator is a simple geometric series, one can sum it very easily. It is an infinite geometric series, one can sum it very easily, and there is a technique by which one can evaluate the numerator from the denominator. I have discussed it in detail in the associated lecture notes. So, I will not go into the detail of the calculation here, but in the associated lecture notes that calculation detail is given. So, we calculate the average energy to be h nu divided by e power h nu by kT minus 1. So, instead of a simple kT in the Rayleigh-Jeans case, we now have a more complicated looking expression, and we borrow the number density that Rayleigh-Jeans have calculated and multiply it with this average energy, and we find that the energy density as a function of frequency is 8 pi h nu cube by c cube times 1 over e power h nu by kT minus 1. So, if h nu by kT is much larger than 1, then we can ignore the minus 1 in the denominator, and we have the formula derived by Wien, which says the energy density should go as nu cube times exponential minus some constant nu by kT, and if h nu by kT is much less than 1, then that e power x I write it, approximate it as 1 plus x, and you find that we recover the Rayleigh-Jeans formula. So, that way Planck's formula number 1 fits the data perfectly, and in the low frequency or high wavelength regime it goes to the Rayleigh-Jeans formula, and in the high frequency or low wavelength regime it goes to the Wiens formula. So, in that sense the tension that I mentioned before was resolved by Planck by his hypothesis that the walls in the black body, which consists of assumed to be oscillators, they emit radiation in quanta either h nu or 2h nu or 3h nu, etc. If you make this instead of a continuous function, you say it is a step function like this, then the tension that was there before between Wien and Rayleigh-Jeans, it got resolved, and you have a nice description which fits the black body data very well. And there is a further bonus. If I integrate the energy density over the full frequency range, you find that the final answer is some function of speed of light, Planck's constant, Boltzmann constant, etc., multiplied by t power 4, which is the Stefans law. So, we are able to derive Stefans law from Planck's law, and not only that, we can predict the value of the Stefan-Boltzmann constant in terms of the fundamental constants of Planck's constant, speed of light, and Boltzmann constant. So, for all these reasons, the Planck's hypothesis was widely accepted, and people started wondering what are the further consequences of this Planck's quanta. Well, further consequence came quite soon, in fact, that is in the form of photoelectric effect. Heinrich Hertz, whose name we remember because the unit of frequency is Hertz, and the reason why that is he is the person who used Maxwell's electromagnetic theory and created man-made electromagnetic radiation in a lab by sort of making charges oscillate, and this man-made radiation we now call radio waves, which of course are used widely in communications. He also did a number of other experiments, and in one of which he discovered that when ultraviolet light falls on a metal, the metal emits some radiation, and when people studied these radiations, they found it actually is set of charged particles which turned out to be electrons, and since they are emitted in response to light falling on the metal, they are called photoelectrons. A little later, a German physicist called Leonard, he studied this photoelectric effect in great detail, and he found that there are some important properties of these photoelectrons which were a bit strange. Point number one, photoelectrons are emitted only when the light falling on the metal is above certain critical value. If the frequency is below, no photoelectrons. If the frequency is above, you had photoelectrons emitted. But if you keep the frequency fixed, the number of photoelectrons was more if the intensity of the light is more. Third point is, they found in order to measure the speed of these photoelectrons, they tried to design an experiment where you try to stop the conduction of these electrons by applying an electric potential. So, once this potential reaches certain level, the photoelectrons stop moving, and that is called stopping potential. And Leonard found that the stopping potential is independent of the intensity, and it depends only on the frequency, and it is larger for larger frequency. And finally, there is no time delay. The ultraviolet light falls and immediately the photoelectrons are emitted. And you try to explain these observations made by Leonard, and it is very difficult to do so. And these two figures, they show briefly what I was telling about. So, you have in the left figure, you have light of two different intensities. So, the photocurrent is more when the intensity is more, but the stopping voltage is the same for both intensities. That is point number one. And in the other, you see the maximum kinetic energy of the photoelectrons. You find that there is no emission for frequencies below f0. For frequencies above f0, there is emission, and the maximum kinetic energy increases linearly with respect to the frequency. And you try to explain it using wave theory, and it turns out that you completely fail, because in wave theory the energy of a wave or energy of radiation is characterized by intensity. If the intensity is more, the wave is carrying more energy. So, I have a low frequency, let us say I have a visible light of great intensity, but that does not lead to any photoelectrons. On the other hand, I have ultraviolet light of low intensity, and that leads to photoelectrons. So, how do we explain this? Certainly, visible light of great intensity is carrying more energy than ultraviolet light of less intensity, but visible light is not producing photoelectrons, whereas ultraviolet light is producing photoelectrons. How do you explain that? And let us look at this point of time delay. How does an electron or an atom absorb energy? The amount of energy absorbed is intensity multiplied by area of the atom times the time interval in which the radiation is falling on the atom. So, let us calculate how long will it take for an atom to absorb enough energy to push out an electron. Sodium, it has what is called a work function of 2.28 electrons, that is the binding energy of an electron in sodium. And if you have light with very small intensity of 10 power minus 7 milliwatts per centimeter square, then you have emission of photoelectrons from sodium. But if we use the classical formula about energy being equal to the intensity multiplied by area of the atom multiplied by the time of exposure, we find that the sodium atom has to be exposed to light of this intensity for almost 100 days before it absorbs enough energy to push out one electron. Whereas, as soon as the light, this light of appropriate frequency falls on sodium, without any time delay, the electrons are coming out. So, how do you resolve these tensions? If you apply wave theory, you cannot explain the fact that there is why there should be a critical frequency. You cannot explain the fact that without time delay the electrons are coming out. And here Einstein comes in and explained the features that were observed by Leonard, and in doing so he used Planck's picture of a quantum, and not only that, he made a further important step. Planck was interested in explaining blackbody radiation, and to do that he made the assumption that energy is emitted in quanta, and he said the quantum can be h nu or 2h nu or 3h nu, 4h nu, it does not matter to Planck. It should be some integer multiple of h nu, that is what Planck said. But Einstein went one step further. He said no, you can't quite do that. So, his argument, which again is based on thermodynamics, is the following. Roughly, suppose I have certain gas of certain mass, capital M. I do not know what it is made up of. So, I can think that it is made up of Avogadro number capital N times a atom of mass M, or equivalently it can be only half Avogadro number, but each atom with mass 2m. In both cases, I get total mass m. But if you have studied any even basic thermodynamics, you would know that behavior of Avogadro number of atoms is very different from behavior of half Avogadro number of atoms. So, by an appropriate study of thermodynamical properties of these two gases, one can tell whether it is Avogadro number times m or half Avogadro number times 2m. And Einstein made similar argument with respect to Planck's quanta, and he insisted that if the radiation has frequency nu, then the corresponding quantum must have energy h nu. Then how do you explain Planck's 2h nu? Einstein said if the energy is 2h nu, it is not a single quantum of energy 2h nu, it is two quanta each of energy h nu. Similarly, if it is energy 4h nu, it is not single quantum of energy 4h nu, it is not two quanta of energy 2h nu, it is actually 4 quanta of energy h nu. So, Einstein sort of firmed up Planck's hypothesis and declared that a quantum must have energy h nu, and if you have 2h nu, it means that there are actually two quanta, and he labeled these radiation quanta photons. And if you want a pictorial way, this is how you should think of a photon. And with photon hypothesis, we can explain photoelectric effect, all the features of the photoelectric effect. So, if wave has frequency nu, it has energy h nu, and unless h nu is greater than the binding energy of electron, it cannot release it. So, that explains the critical frequency. And the time of absorption for an electron to absorb a photon, later quantum mechanics tells us that it is like a nanosecond. So, there is no time delay, and the kinetic energy, the stopping potential is related to the maximum kinetic energy of the electron, and that is related to h nu minus the work function. Therefore, it is completely independent of intensity. So, that is also explained. And not only that, we also see that we have this nice linear relationship between the frequency and the stopping potential. So, Millican did a large number of experiments where he measured the stopping potential as a function of frequency and saw this linear potential, which was predicted by Einstein's explanation. And in fact, he measured Planck's constant by measuring the slope of this linear relation. I conclude by posing a question for you. Think about it. I will answer it in the next class. That is, what if the frequency is low, why can't the electron absorb two photons and be released? Why are we saying that the electron should absorb one photon to be released? In the case of low frequency, why can't electron absorb two photons and be released? I mean, if we are talking purely in terms of energy, that should be possible, but we don't see it happening. So, we must have an explanation as to why that should be so. So, you think about it, and we will discuss it. I will briefly talk about it in the next lecture. Thank you.